Distributed Systems from Scratch. This is episode 15, System Design Patterns, the season 3 finale. This is the synthesis episode, 14 episodes of theory, protocols, and systems, all coming together on a whiteboard. Every episode in this series has been building toward this moment. Season 1 gave you the vocabulary, partitions, clocks, consistency. Season 2 gave you the algorithms, consensus, replication, partitioning. Season 3 showed you real systems, GFS, Kafka, Flink. Now we combine everything. We are going to design three complete distributed systems from scratch. And at every decision point, I'll connect back to the specific episode and protocol that guides the choice. Every system design follows three steps. Step 1, Requirements. What does the system do? What are the functional requirements? The features, and what are the non-functional requirements? Latency targets, throughput, durability guarantees, availability, SLA. Step 2, Estimation. Back of envelope math. How many requests per second? How much storage over 5 years? How many machines? These numbers drive every architectural decision. Step 3, Architecture. Choose your components: storage, caching, queuing, processing. Connect them, identify the bottlenecks, then apply the protocols from seasons 1 and 2 to solve each bottleneck. Here are the numbers you need for estimation. Memorize these. There, your design toolkit. Storage. A character is 1 to 4 bytes. A tweet with metadata is about 300 bytes. A thumbnail image is 200 kilobytes. A full resolution image is 2 megabytes. Throughput. An SSD reads sequentially at about 500 megabytes per second. A 1 gigabit network link gives you about 100 megabytes per second. Redis handles about 100,000 operations per second. Latency. The same numbers from episode 1. RAM is 100 nanoseconds. SSD is 100 microseconds. Same data center is half a millisecond. Cross continent is 200 milliseconds. And for scale math, a day is about 86,000 seconds, roughly 10 to the fifth. 100 million users making 10 requests per day is about 12,000 queries per second average, 36,000 at peak. Rule of thumb: a single modern server handles 10,000 to 50,000 simple queries per second. Need more? Partition and replicate. Design 1, a URL shortener like bit.ly or tinyurl. This is the simplest distributed system design, but it touches almost every concept in the series. Here's the architecture: the write path. A client sends a long URL. The request hits a load balancer, which routes to one of n stateless application servers. The app server generates a unique short ID. We'll use something like a snowflake ID or a counter with base 62 encoding. It stores the mapping, short URL to long URL, in a sharded database and returns the short URL to the client. The read path: a client requests a short URL. The app server first checks a Redis cache. Hot URLs are cached for fast lookup. If it's a cache miss, it queries the database. Either way, it returns a 302 redirect to the long URL. Why 302 and not 301? A 301 is permanent. Browsers cache it, and repeat clicks never reach your servers again. Your click analytics silently die. A 302 keeps every click flowing through you. This little detail is a favorite system design interview trap. For analytics, every click event is published to Kafka. A Flink job aggregates click counts, referrals, and geographic data into a dashboard. The database is sharded by hash of the short URL, consistent hashing from episode 9. Each shard has a leader and two followers, replication from episode 8. Let me map each decision to a specific protocol. ID generation: Snowflake IDs combine a timestamp, machine ID, and sequence number. They are unique across shards without coordination. This connects to ordering from episode 3 and partitioning from episode 9. Caching: Redis for hot, URLs. The 80-20 rule says 20% of URLs get 80% of traffic. Cache aside pattern. If the cache goes down, we degrade gracefully. Just hit the database directly. Fault tolerance from episode 10. Sharding. Hash the short URL and use consistent hashing for assignment. When we add a node, only 1 over n of keys move. Episode 9. Replication. Leader follower per shard. Asynchronous replication is fine here. A stale read just means an occasional 404 that resolves on retry. Not dangerous. Episode 8. Analytics. Click events flow to Kafka, then to Flink for windowed aggregation. Real-time click counters. Episode 14. Design 2. A distributed cache. Think Redis cluster, but from first principles. This design is almost entirely about partitioning and failure handling. The architecture is a consistent hash ring with cache nodes. The client library hashes each key and routes directly to the owning cache node, no proxy in between. Client-side routing for minimal latency. The ring uses virtual nodes, 256 per physical node, to smooth out the distribution. When a node dies, gossip-based failure detection from episode 12 notices. The keys that belong to the dead node are rehashed to its clockwise neighbor. Clients update their partition map. Eviction is L R U per node. Least recently used items are evicted when memory fills up. Cold start is a real problem. When a new node joins or a node restarts, its cache is empty. A thundering herd of cache misses hits the database. The mitigation is cache warming. Preload hotkeys from the database before the node starts accepting traffic. The key design decisions are consistent hashing from episode 9, gossip based failure detection from episode 12, and circuit breakers from episode 10 to protect the database during cache failures. Design 3. A chat system at WhatsApp scale. This is the hardest design here. It combines networking, ordering, storage, streaming, and presence management. Here's the architecture. Users connect via WebSocket to a gateway server. The gateway maintains persistent connections and tracks which user is connected to which gateway instance. When user A sends a message, it flows to the gateway, then to the chat service, which publishes it to Kafka, partitioned by conversation ID. This gives us ordering within each conversation. From Kafka, two things happen. The message is stored in Cassandra, partitioned by conversation ID, clustered by timestamp. This gives us efficient retrieval of message history, and the message is routed to user B's gateway server for real-time delivery. If user B is offline, the message stays in Cassandra. When B reconnects, the gateway fetches unread messages from the database. A push notification service handles mobile notifications for offline users. Presence, online/offline status, is tracked in Redis. Each user's status is updated on connect and disconnect with a TTL for crash detection. Mapping the decisions. Real-time delivery uses WebSockets. Persistent TCP connections from episode 1. The gateway routes messages to the right server. Message ordering uses Kafka partitions keyed by conversation ID. All messages in a conversation go to the same partition, giving us strict ordering within that conversation. Episode 3. Ordering. Episode 14. Kafka. Storage uses Cassandra with its LSM tree engine from episode 13. Partition key is the conversation ID, clustering key is the timestamp. This makes fetch the last 50 messages in this conversation a single efficient query. Consistency model is eventual consistency from episode 5. This is fine for chat. A message appearing a second late is acceptable. Causal ordering within a conversation is handled by Kafka's partition ordering. Now let me show you the recurring architectural patterns, the building blocks that appear in virtually every distributed system design. CQRS, Command Query Responsibility Segregation. Separate the write path from the read path. The write model optimizes for writes. maybe an event log or a normalized relational schema. The read model optimizes for reads, denormalized, pre-computed views, maybe in a different database entirely. An event stream synchronizes the two. When a write happens, an event is published. The read model consumes the event and updates its views. Why? Because reads and writes have fundamentally different characteristics. Writes need ACID, strong consistency, careful validation. Reads need speed, flexibility, different query patterns. Trying to optimize one database for both is a losing game at scale. Event sourcing. Instead of storing the current state, store every event that led to the current state. Traditional approach. Update account set balance equals 800. History is gone. Why is the balance 800? Nobody knows. Event sourcing. Store the events. Deposit 1000. Withdraw 200. The current balance is derived by replaying the events. 1000 minus 200 equals 800. Full audit trail. You can rebuild any view from the events. You can time travel by replaying events up to a specific point. The Kafka log from episode 14 is an event store. Combine event sourcing with CQRS and you get a powerful architecture. Events are the write model, materialized views are the read model, and Kafka connects them. Three more patterns worth knowing. Cache aside, the standard caching pattern. On read, check the cache. Miss, read from the database, then populate the cache. On write, update the database, then invalidate the cache. Simple, effective, and used by virtually every web application. Sidecar and service mesh. Instead of implementing retries, circuit breakers, and TLS in every service, attach a proxy sidecar to each service. Envoy and Istio do this. All the fault tolerance patterns from episode 10, retries, circuit breakers, bulkheads, implemented once in infrastructure, applied everywhere. The outbox pattern, when you need to write to a database and publish to Kafka, don't do both separately. That's a dual write and one can fail. Instead, write to the database and an outbox table in a single local transaction. A background process reads the outbox and publishes to Kafka. Solves the consistency problem from episode 11 without 2PC and 4 common anti-patterns. Distributed monolith. You've decomposed into microservices, but they all deploy together, share a database, and can't function independently. You have all the complexity of distributed systems with none of the benefits. Premature partitioning, sharding your database before you need to. A single PostgreSQL instance on modern hardware handles far more than most startups will ever need. Don't shard until you must. Dual writes, writing to the database and Kafka separately. If the database write succeeds but the Kafka publish fails, or vice versa, your data is inconsistent. Use the outbox pattern instead. Ignoring the network, treating remote procedure calls like local function calls. Every call can fail, be slow, or return stale data. The 8 fallacies from episode 1 are alive and well. Here's the meta insight of this entire series. Every distributed system is a composition of the same small set of primitives: partitioning, replication, consensus, caching, and messaging. The art isn't knowing the primitives. After 15 episodes, you know them. The art is knowing which ones to combine for a given set of requirements and which trade offs to accept. A URL shortener composes hash partitioning, leader follower replication, cache aside, and event streaming. A chat system composes WebSockets, Kafka partitioning, Cassandra storage, and gossip based presence. Different combinations, same building blocks. This is how all distributed systems are built. Season 3 is complete. Episode 13, Distributed Storage. B trees versus LSM trees, GFS and HDFS. Bigtable and its descendants. The Storage Foundation. Episode 14, Stream Processing. Kafka as the distributed log. fleeing for stateful stream computation, event time, watermarks, and exactly one semantics. Episode 15. Today, system design patterns. 3 complete system designs: CQRS, event sourcing, and the recurring patterns, anti patterns to avoid. 3 seasons down. We've covered the theory, the protocols, and the systems. The foundation is complete. Final takeaways: 1. Start with requirements, then estimation, then architecture. Back of envelope math drives every design decision. 2. Every distributed system combines the same primitives: partition, replicate, cache, queue, process. Learn the primitives and you can design anything. 3. CQRS separates read and write models. Event sourcing stores events, not state. Combine them for powerful architectures. 4. Avoid the anti patterns: distributed monoliths, premature sharding, dual writes, and ignoring the network. 5. Start simple: single node, add caching, add replication, add partitioning. Scale when you're forced to, not before. Season 4: Advanced Topics, Beyond the Fundamentals, Into the Frontier. Episode 16: CRDTs, Conflict Free Replicated Data Types, Data Structures that Merge Automatically Without Conflict. The Mathematical Solution to Multi-Leader Replication from Episode 8. Episode 17: Geo-Distributed Systems, Google Spanner, TrueTime, and the engineering required to maintain consistency across continents. Episode 18: Byzantine Fault Tolerance, PBFT, Hot Stuff, and how blockchain consensus actually works. What happens when nodes can lie? That's episode 15 and the end of season 3. System design patterns, the synthesis of everything we've learned. 3 seasons complete, 15 episodes, from the two generals, problem to designing real systems. Season 4 starts next. We go deeper. Thanks for watching.